All right, well, it is 32 past the hour. Seems like most people are from, there are two from Toronto and one from New Jersey. I'm not sure about the time zone in New Jersey, but it is 1:32 right now here. So we could get started. Before I introduce our next speaker, I'd like to just give a quick reminder for everyone to check out our partners at the booth for where you could enter for a chance to win some great prizes. We had Sonos speakers in the past, so definitely check it out. You could navigate to the booth from the booth buttons on the left. Now, without further ado, I'd like to introduce our next speaker, Xin Li. Xin is a member of AI technical staff at Vector Institute's AI engineering team. Working with the vibrant community at the Vector Institute, Xin collaborates with Vector researchers and industry partners to make deep learning research more accessible in applied settings. Xin will be giving us a talk about deep learning-based lung ultrasound video classification to predict COVID. Please give a warm welcome to Xin Li.
Thank you very much, and welcome everyone. So without further ado, let me present. So I hope you can all see the screen. Unfortunately, I lose the chat window, so if anything, I'll defer the Q&A in the end. So today's talk will be deep learning-based lung ultrasound video classification to detect COVID. So to start off, I kind of want to give you a bit of a background of why this project was started in the first place. So this was started as part of the computer vision project at Vector Institute. So every once in a while, Vector, we would call for our collaborators and researchers to explore new areas of machine learning. So in this case, in computer vision. And then we want to be able to apply a lot of theories in more applied settings. So we kind of gather participants from both our researchers as well as industry collaborators. So in this case, we kind of looked at the problems of anomaly detection, segmentation, semantic segmentation, as well as working with videos for action classification and localization. And of course, we want to be able to focus in kind of different applied settings in health, manufacturing, traffic, or autonomous driving. So this kind of spawned as part of the computer vision project. And at the point of this project, and I mean, until now, COVID is one of the biggest things on everyone's life. So we started looking into kind of these lung ultrasound videos. So essentially, what lung ultrasound is, it's kind of it's a cheap, portable, and kind of easy to sterilize device that can visualize through electromagnetic properties, the activities within your lung. So the advantage of this kind of in comparison to say PCR tests that we always have now is you don't actually require lab testing. So you kind of go into a point of care facility, usually equipped with these equipments, and get it tested. So in theory, it has a faster turnout time for a single test. And it's generic, right? It's not only indicative for, let's say, COVID, where it was previously used to kind of detect pneumonia and other lung-based respiratory diseases. So this is not to kind of say, okay, this can replace the current test we do for COVID patients, but we can further assist risk stratification based on the additional properties you can potentially visualize from these lung ultrasound. And just on a side note, as technology progresses, these devices are now extremely portable. You can have a device that literally plugs into your phone, or maybe even remotely to have a kind of a doctor look at the conditions based on these portable lung ultrasound devices. So how is it anything to do with deep learning and all these other things? So first of all, lung ultrasound is represented to clinicians as videos. And through over the years, there has been a lot of progress made in the image space, right? The AlexNet, ResNet, and vision transformers up until now. But similarly, there's a lot of progress also made in video space, right? Because a lot of the findings that people do find in the 2D or in the image space transfer quite well into videos. So you would still kind of apply deep convolutional neural networks, but now your modeling techniques usually adapt from 2D to 3D. So convolution as an operator is, it can be applied in two-dimensional, and it can be applied as a three-dimensional filter, right? You kind of go as a cuboid. So what changes now is your input before, which was let's say an image, now includes a temporal dimension. And now with that input change, there has been like a lot of effort in the modeling side of things. So people started with LSTMs kind of to sequentially feed these images into ConvNets, to classify actions. And then eventually people trying to, just feed the entire thing into a 3D convolutional neural network. And there are kind of techniques adapted into having multiple streams of inputs to your neural networks, just to model different types of semantics, right? You can have motion level or maybe picture level semantics that you want to be able to capture in these different streams. So, all after all, a lot of progress have been made in the video space, but as we all, as the literature kind of suggests, a lot of the progress was made on action classification, right? So we kind of model, people jumping around, people running, and then we want to be able to classify these actions. It's very analogous to people doing a lot of optimizations in ImageNet classification training tasks. So now moving on is, given that COVID ultrasound videos are videos and they kind of also present us these temporal signs of COVID patients, is there a method where we can actually adapt existing deep learning techniques that was used to be done on action classification to detect signs of COVID, pneumonia, or maybe other normal lung ultrasound videos, and then kind of help us in the sense that we can maybe devise a deep learning model to automate or assist in some of the diagnosis of lung ultrasound videos. So the immediate first step you think would be a classification task, but eventually, for these tools to be really helpful, you want to be able to both classify and provide a bit of spatial temporal localization to the task to actually pinpoint, the locations of some of the anomalies or very obvious characteristics of these lung ultrasound videos that hints, certain diseases or symptoms. So a bit of a disclaimer is that this project is not developed. This project is only developed as a proof of concept for exploratory purposes. So none of our methods or results have been kind of clinically proven, verified, or applied in a clinical setting. So this is not also an endorsement or advocate for the methodology to be applied tomorrow in a hospital, right? So we just want to see if taking the existing advances in action classification, does the techniques transfer well to medical videos of lung ultrasound. So this I'd like to start with a demo, right? So we have also put the code in this link. So if you get a shareable presentation, you should be able to click and navigate to this GitHub repository. So again, what we want to be able to visualize or show you here is a few of the examples and a few of the predictions and kind of some insight on what the model did. Again, so the first thing is training data, right? We want to be able to train a deep learning model. So the data set we used is COVID-X US. So it says US, but it's an open access benchmark data set for COVID-19 related ultrasound imaging data. So it's actually initiated here by University of Waterloo and INSERC. So this data set was curated from multiple sources. So there's these point of care facilities. There's also these medical equipment providers. They kind of chipped in and provided 173 lung ultrasound videos. And they kind of include all different classes of COVID-19, pneumonia, normal lung ultrasound videos, and other, where it's unspecified. So the class is somewhat balanced, with the exception of normal and other. Then after getting the data, it was then systematically processed and validated by health professionals. So the data annotation is actually done by health professionals. And ultimately, we kind of prop into more squarish videos and then feed it to the model. So you can read more about this data set, but as you can see, also one interesting thing to note is the data set contains two types of ultrasound. One is convex, which is you see with more of a convex lens, and there's a linear, which is more kind of it's a different imaging technology essentially. So I'd like to show you first of all a few data samples. So in a normal or maybe unspecified lung ultrasound video, this is what it would look like. Again, not being a health professional, I'm not going to comment any kind of signs or symptoms that hints this, but I do want you to kind of take a note of whether there are interesting characteristics of these videos. So a COVID ultrasound video kind of has a bit more, at least from a first glance, moving components, and finally a lung ultrasound of a pneumonia patient would look slightly different as well. So this is just to give you a bit of a impression of what these different lung ultrasound kind of looks like. So we've hence developed a few modeling. So I guess we can start with selecting a model. So the simplest model we can get, which is a kind of a benchmarking model, is a ResNet 3D model. So as you all know, the residual networks in the 2D space is quite popular, and it's used as a de facto benchmarking model for image tasks. So the 3D model is kind of you adapt all the modeling techniques in 2D and inflate it into 3D. So now your input is no longer an image, right? It's instead a 4-dimensional tensor, right? It includes time, height, width, and channel, right? Channel usually is RGB. So now with this 4-dimensional input, you kind of go through, instead of 2-dimensional convolutions, 3-dimensional convolutions. And then it's not shown in this picture, but in the ResNet case, you would have skip connections and bottlenecks, throughout. And then finally, it has a space and time pooling, followed by a fully connected layer for the final classification. So you kind of have the same ideas, but in the 3D. And a slight improvement of the model is what's called a mixed convolutional network. So the hypothesis is that motion modeling may be particularly useful in the earlier layers, but motion or temporal modeling is not necessary in the later layers. So architecture could kind of start with a 3D convolution and then swap a few of the convolutional layers in the later stages into 2D convolutional, because it's just not necessary to model these kind of first or like earlier abstractions in the input. So we kind of train these two models because so we fine-tune these models on kind of existing the model weights that was actually trained on excellent classification. So one big limitation we had with the data set was ultimately it was a really small data set. So after loading it, we had to apply a lot of data augmentation, such as rotation, translation, flipping, as well as a bit of a color jitter, just to kind of enrich the data space, because we're working with such a small data set, and also to kind of deal with a lot of the overfitting problem of this such small data set. We had to do a bit of a lot more regularization into our training pipeline, right? You kind of had to tune the values of your dropout, tune the values of your weight decay, et cetera, such that you're not kind of resulting in a model that overfits too much, just because you're working with a fairly small data set compared to what it was pre-trained on, right? It was pre-trained on a kinetics data set with tens of thousands of videos before. So one thing was that, and also because you're working with a very small data set, your validation set also could introduce a bit of bias. So we had to adapt the validation process into a 5-fold cross-validation, just because we want to be able to leverage all the data set for training, but we'll also be able to come up with a reasonable validation score that's not biased, right? That's somewhat based on the entire data set. So this is some of the technical details, and ultimately, we arrived at some good candidate models, and we can kind of show you as a result of how they do. So here, we've selected this mixed convolutional network as our model. So you can play this video. This is from the test set, which has not been kind of looked at before, and I here can take a guess. Doesn't look like anything similar from what I saw, so maybe this is a normal or some other ultrasound videos. So you can test the video against the model. It'll give you some predictions, and it predicts with 74 confidence that this is the kind of a normal lung ultrasound video. And as it turns out, both of us are correct. So you can look a few more, right? You can look at this one. So I'm seeing these bright lines that kind of looked familiar. I believe in technical terms, they're called B lines, but I'm not going to comment further. So again, making my wild guess, and it seems that both of us are correct. And finally, I'm just picking one example each, so it does seem kind of obvious what the third one will be. But this one looks like a lung ultrasound video for a patient with pneumonia. And you can also test video against the model. This one actually, predicts with very high confidence that this is a ultrasound video of pneumonia patient, and it would be. So this is the end of the demo, just to give you a bit more concrete numbers on the results. So going back to presentation, so we did 5-fold cross-validation for 2 of the models that we kind of did a hyperparameter search for. Remember, we had to do a lot of regularization. We actually attempted adaptive loss scaling to deal with a bit of the data imbalance. But ultimately, what we were able to arrive at is a 87% validation accuracy on one of the models. And then because it's 5-fold cross-validation, the standard deviation of the 5 validation results were 3.2%. So there were kind of a few candidate models, but this model was consistently behaving or performing well enough to our expectation. So this was ultimately chosen as one of the final model that you just saw. And the test accuracy turned out to be a little bit less than the validation, so it's 82.6. But and then we can kind of look for the more interesting metrics of precision and recall of COVID, as well as the confusion matrix in general on the right. But it does seem that the model performs well enough to an exploratory standard of 89%. So yeah, I'm missing a lot of the details, and I'm hoping to kind of talk about this in our QA and discussion. That would be it for this presentation.
All right, awesome. Thank you so much, Xin, for the fascinating talk. We definitely have a couple questions. Um, so yeah, to start off, was there any work in screening for the bias in the data set provided?
Um, yes, actually, so we haven't been able to look into this yet, but we believe um, so. From a very start, when I was pre-processing the data, I kind of looked at a few samples, and it does seem like each of the providers would have a very specific um, texture attached to it. As we all know, like the convex and linear lens is already quite different in the way they present these images. But even in different medical providers or equipment manufacturers, they have also introduced their own flavors. So I was initially a little bit worried about how this would affect the model performance. We didn't do a systematic analysis, but what we did end up doing was, we tried to do a lot of more data augmentation that gets rid of the things that are not suggestive to the actual symptoms. It's more of a best effort thing, but there are definitely biases in the data set.
And I guess kind of follow up to a bit more about the data set. Were all the videos the same duration and time, or because once you kind of go into inference space, how would that work?
So no, all the videos are different length. So what you end up doing is your final spatial temporal pooling would adapt to the final latent vector that you want to be able to feed into the fluid layer. So let's say it was a long video, then your final spatial temporal pooling would kind of pull with bigger steps than if it was a shorter video. This is to actually, so there are people who chop off videos and have it fixed sized. There's of course different trade-offs at inference time. So in those cases, you kind of, what you do is you average the predictions of the three crops and then you kind of give out the final prediction there.
Mm-hmm. Okay. And our next two question is more specifically about the model selection and a bit more about the model that was selected. So the first one is, did you try using transformer-based models?
So no, but it would be an interesting idea because then you might be able to visualize a bit of the attention rest to understand more from a explainability perspective. We didn't do it because we also had a bit of a compute budget. So these models are more kind of more economic choices for us. But yeah, definitely would be interesting to look at.
And I guess a bit more about the 3D Cov model. Don't we always apply a 3D filter on RGB? What's the difference for videos?
Yeah, so when you apply 3D filters on RGB, you actually apply, so it's actually a 2D filter, but you apply many filters on these, right? If you remember correctly, let's say for the first layer, your input channel is 3, your output channel is 5. You would actually have, kind of 5 of these filters going into 3 of the input channels and producing 5 output feature maps, right? So that's actually a 2D filter, but you have 5 of these 2D filters. So I wouldn't say them as 3D comps. The way you do in 3D is you just increment every number by 1, right? Your convolution before you can imagine as a sliding window, right? Across your X and Y axis. Now it will be a sliding cuboid, right? So it would actually slide across X, Y, and Z axis of, you can imagine your video being a cuboid thing. It actually will produce another cuboid, in the output feature map. So
that makes a lot of sense. And our last question, or actually our next question, we have more, is talking more about the, I guess, what data set to use. Is ultrasound common in COVID diagnosis, or is it better to use X-rays?
So I'm not an expert in the health space. So X-ray, I believe, is more of an image-based, and ultrasound is more of a reflection or like a wave-based response. So although it both ends up as video or imaging from like a normal user, but the technology that's used to generate images is different. So that's one thing I know about. The thing about ultrasound that I found different was, if you think about the CT scan or X-ray, you kind of had to go through this large equipment, and you had to have a lot of prep time for such examinations. But the ultrasound machines are more kind of a bit easier nowadays with the technology improvements.
I see. And you mentioned earlier that ultrasounds are very used. It's very cheaply to use, right? Deployable. So I guess a little bit back on about the transformer model. How can you apply that to videos?
So I think a technique that you would do is, usually you kind of have these 16 by 16 patches of your original input, and you fed them sequential as sort of so imagine the transformer cases, you had the tokens, right? You kind of tokenize your input. So I think that the method you would do is you patch up your images, and you kind of treat them as tokens in the transformer, and then the transformer would use the attention layers to kind of find the relationships there. Yeah,
I see. That's a really interesting implementation. Definitely will look more into that. And I guess our last question is, are there any next steps for your model in this space?
I think for health, like one thing we need, so that's why we did the disclaimer. One thing that's particularly important is explainability. Like, can you explain the 89% that you got? Like, what does it mean? Like, what did it get right and what did it get wrong, right? So there are a lot more technologies nowadays on deep learning model explainability. You can kind of visualize saliency maps. You can do GradCam to visualize where the model is basing its prediction on. So that's one of the things we want to be able to look at. And after that, you can actually devise a bit more feature of your model, right? You can say, this is my prediction, this is what I'm basing my prediction on. So because ultimately we're not using this as a safety critical component, right? Like, we may be able to use this as some assistive technology to clinicians, right? So you want to be able to provide as much information as you can to that process. So I think that would be a next step for this.
Yeah, definitely makes a lot of sense, and that would be a very exciting next step to be able to have a lot more explainability and being able to implement that. So yeah, that should be it for the questions. Thank you again, Xin, for this amazing talk, and thank you everyone in the audience for tuning in.